Alright, I'm making an extra video. Just I don't want to deprive anybody if they want to learn this last one and practice coming up with your own formula, because I do think there's some merit in being able to find a formula. So what I typically do when I do a problem like this is I look for a pattern. So for instance, the first sum is, I think that's pretty clear that the first sum is just going to be 1/2, because 1 times 2 is 2, so 1/2. So then the next sum is going to be whatever 1/2 plus 1/6 is, because we're adding these two numbers together. And what we're trying to do is come up with a pattern that would give us the formula. So as I'm doing this, I would probably change this to be 3/6, and 3/6 plus 1/6 is 4/6. So the second sum is, well, that reduces to 2/3. And so when I look at the third sum, that would be adding the first two together, which we already did, was equal to 2/3, and we need to add to it 1/12, which I like how they set it up, because clearly there's a pattern between 3 to get to 3 to get to 12, and that's by multiplying by 4. So this problem's a little bit easier than the one I would have assigned in the homework, but this would have been 8/12, and if I add that together, 8 plus 1 is 9/12, which reduces to 3/4. So I think this pattern's a little bit easier than again the one I come up with, or I ended up assigning in the homework that I'm asking you to skip now. That there's definitely a pattern to go from 1/2 to 2/3 to 3/4. And if you're not sure, you could even try the next one. You know, is it still true that 3/4, the sum of the first three, plus the next one, which would be 1 over 4 times 5, so it would be 1 over 20. Is that equal to, if you're thinking the next answer is 4/5, well, just double check. If you got the same denominator, it would be 15/20 plus 1/20 is 16/20. And yes, it does reduce to 4/5. So there's definitely a pattern. And that pattern was supposed to say that, you know, for the first sum, the 1 on top is because it was the first number, and the 2 came from, well, that was the next number from it. So the sum of the first two terms is 2/3, because 2 for the two terms, and 3 is 1 more than that. The sum of the first three terms, 3 on top, because that's the number term it is, and then 1 more than 3 on bottom, n plus 1. And then the first 4 terms, n on top, and then n plus 1 on bottom. Excuse me. So now what we can do is we can prove that this is the right formula, and sometimes it's just a lot of guessing and checking. I do realize that guessing and checking is a strategy, and now we can prove it by doing induction. That's what I meant by prove its validity. You can use mathematical induction to prove that it's true. So I like to go to this piece of the formula and plug in 1 in for those ends. 1 plus 1 is 2. So we're looking at 1/2 there. And then if I plug in 1 in for these ends, I get 1 over 1 plus 1 is 2. And some people might actually show a little bit more work than what I just did right there. But you can say, hey, that is true. Since 1/2 equals 1/2, the base case is true. And then from there, you can do your inductive step. Remember, we're doing n equals k plus 1. So as a reminder, you'll see me write it out like this. I rewrite the same thing. 1 over 1 times 2, over 1 times 1 over 3 times 4. I like to rewrite that formula with k's, though. And then I need to add the next term to it. So instead of n here, I need the k plus 1. Remember, we're knocking over the dominoes. And then this n is k plus 1, so it becomes k plus 2. And as a reminder, we want to show that this equals not n anymore, k plus 1 over k plus 2. So as we look at that problem, so remember this piece is equal to, well, instead of n over n plus 1, we have to write k over k plus 1. And then we still have this piece over here, this 1 over k plus 1, k plus 2. And I know I'll do this correctly, well, assuming I have the right formula, if I get to this what to show, what I want to show. So if you look in the left fraction, I'm missing the k plus 2 term. So I can multiply this k by k plus 2. I hope you're okay that I'm distributing that in there. And this right fraction already has the k plus 1 and the k plus 2, so I don't have to change that. So now I have the same denominators. And if you look in the numerator, we can factor that out. I did something wrong, didn't I? I need to multiply this k by k plus 2, so this should have been k squared plus 2k. Now the numerator is factorable. And that's what I like about induction, is by knowing what I want to show, I can tell quickly when I make a mistake. And what you should now notice is that we have a k plus 1 on top and a k plus 1 on bottom that I could factor them out. And lo and behold, I end with what I was trying to show. So what I've done is I've come up with a formula for the sum of finite terms, and then I proved by using induction that this formula actually works for any number of terms. So I could have, done 7 terms, and I know that the final answer would be 7 over 8. I could do it for 100 terms, and I know that answer would be 100 over 101. You can do it for as many terms as you want, and based off of mathematical induction, we can prove the formula works for all cases just by setting up a domino and knocking it over. So I do realize this is an extra video, and if you watched it, I hope you enjoyed something, and I hope you realize that I do recognize that this is difficult stuff. And I'll see you in the next section.